Hello students. In this session, we are going to continue the same chapter, that is organic synthesis via enolates. In the last session, we had discussed what are enolates, then preparation of ethyl acetoacetate is what we had discussed by Claisen condensation. Followed by that, we had also discussed about the keto-enol tautomerism. In this session, we'll be discussing the synthetic applications of ethyl acetoacetate, that is synthesis of ketones, synthesis of carboxylic acids, and then the heterocyclic compounds. So this is what we are going to discuss in this session. So let us start with the first one, that is synthesis of ketones. So hope you all know what are ketones. Ketones are the organic compounds that contains C double bond O group. So where both the parts here are alkyl or aryl groups. Out of these two groups attached, if one is hydrogen, we call them as aldehyde. If both are alkyl groups or aryl groups, we call them as ketones. So ketones have this general formula, C double bond O. Okay, so these are carbonyl compounds. So methyl ketones can be prepared from ethyl acetoacetate. This reaction involves the use of sodium ethoxide. Okay, so ethyl acetoacetate is first treated with sodium ethoxide. So it generates sodium salt of ethyl acetoacetate, and then the molecule is treated with alkyl halides followed by ketonic hydrolysis will give you the required methyl ketones. Let us just deal with the reaction. So hope you know the structure of ethyl acetoacetate. It goes like this: CH3, C double bond O, CH2, COO, I mean C double bond O, O, C2H5. Okay, this is ethyl acetoacetate. Now, so we are going to prepare ethyl ketones from this ethyl acetoacetate. So first, this molecule is treated with ethoxide. Okay, sodium ethoxide. You know that sodium ethoxide is a base. So what it does is it removes the acidic proton, and you know that this hydrogen is acidic in nature because it is flanked in between the two carbonyl electron withdrawing groups. So this hydrogen is acidic in nature. So this hydrogen can be easily abstracted. So the ethoxide ion, it abstracts this hydrogen. When it abstracts this hydrogen, so it results in the formation of an anion. I'll write the structure: CH3, C double bond O. So hydrogen has been removed from here. So proton has been removed. So you get CH minus there, minus. So then C double bond O, O C2H5. Okay, sodium ion neutralizes this, so it will be in the vicinity only. So this is how it can be written. So this is the sodium salt that is obtained. So ethyl acetoacetate is first treated with sodium ethoxide. Sodium ethoxide being a base, what it does, it abstracts this proton. So removal of this proton generates an anion here. This anion is generated. Now, so we want methyl ketones. We are targeting the preparation of methyl ketones is what we are preparing. Okay, now if you want to prepare a methyl ketone, then you need to add a methyl halide to this. I'll write the general reaction now. I mean, alkyl ketones is what I can call it as. Methyl is an alkyl part, so alkyl ketones is what I can call it as now. So what I will do is, this is treated with an alkyl halide, RX. This is treated with an alkyl halide, RX. So you know that RX will be, halogen is electronegative, so this will be slight negative charge and this will be slight positive charge. So this negative charge attacks this, and this halogen atom gets expelled. Okay, so this salt is treated with what? It is treated with an alkyl halide. You know that alkyl halide is a polar molecule where the halogen part is negative charge and this is the positive charge part. So this negative charge attacks this, and this X gets expelled. So there will be a bond formed between this carbon and R. Okay, and this gives you this compound. I'll just write the structure of that compound. You get CH3, C double bond O, CHR. There is a bond formed, so it will be C double bond O, OC2H5. This is what we are going to get. So from where this R came, see what we have done is, we have used sodium ethoxide, we have abstracted a proton, the negative charge generated, it is treated with alkyl halide, so the positive part of the alkyl group, this negative charge attacks this, resulting in the formation of a bond. Okay, this is what we have obtained. Now, this is subjected to ketonic hydrolysis. Okay, it is in presence of dilute HCl, and next it is heated or warming is what is done. So what generally happens is here, when you treat it with dilute HCl, hydrolysis takes place. So hydrolysis takes place and this bond cleaves. Okay, you get H here and a OH here. H, OH. So you get a carboxylic acid. So this molecule goes as ethanol. That molecule goes as ethanol. So you get C2H5OH as the side product. So HOH. Okay, you get a carboxylic acid here. When it is heated, decarboxylation takes place. Decarboxylation matlab removal of carbon dioxide takes place here. So you have C double bond OH here, because H is added here and OH is added here. So this C2H5OH is what you got, and you get a carboxylic acid. Whenever it is heated, carbon dioxide is removed. So what will be remaining? The part that will be remaining will be this one. So this goes as carbon dioxide. This will remain. HR. So carbon dioxide goes off, and what you get? You get a H here. This is what you get, a ketone. So this can be written as like this: CH3, C double bond O, CH2R. So this is how we can write it as. Are you getting this? So alkyl part attacks here. So this is what you get. When it is treated with dilute HCl, it undergoes hydrolysis. So this bond breaks. So you get an alcohol as a side product, and OH attaches here. When it is heated, loss of carbon dioxide takes place. CO2 goes here, and what you get? CH3, C double bond O, CH, the H of an acid, CH2, R is what you get. So this is the ketone that you are going to get. Okay, this is the method of preparation of ketones by using ethyl acetoacetate. Okay, now next let us go for the preparation of carboxylic acids. So carboxylic acids, monocarboxylic acids can be easily prepared by acid hydrolysis. Okay, so simple acid hydrolysis will give you carboxylic acids. Let us discuss the acid hydrolysis of that. Let us discuss the acid hydrolysis of this compound right now. So what is done is here, acid hydrolysis. So synthesis of carboxylic acid. Synthesis of carboxylic acid. Hope you know what are carboxylic acids. Carboxylic acids are the compounds that contain C double bond O, OH groups are generally referred as carboxylic acids. Okay, simple hydrolysis, I mean acid hydrolysis will give you carboxylic acids. Right, I'll just write ethyl acetoacetate. This is ethyl acetate, CH3, C double bond O, CH2, C double bond O, OC2H5. Okay, this is ethyl acetoacetate. Hydrolysis. 2 molecules of water will be used. You will come to know why 2 molecules. Okay, hydrolysis. Okay, in presence of concentrated NaOH, okay, and then dilute HCl or H2SO4. Okay, so first it is treated with concentrated NaOH and then with dilute HCl. See what happens is here. Okay, this undergoes hydrolysis. Okay, now when it is hydrolyzed, this bond breaks. H adds here, OH adds here. Okay, this bond also break. OH adds here and H adds here. So when ethyl acetate is subjected to acid hydrolysis, so this carbonyl carbon and the next bond breaks. So this bonds breaks here, it will be H, OH will add here, this bond breaks and H and OH, resulting in the formation. This is one molecule you get. C2, H5, OH you get. Okay, what will be remaining? CH3, C double bond O, OH. CH3, C double bond O, OH. Here also you get CH3, C double bond O, OH. 2 molecules of acetic acid is what you get. Okay, simple hydrolysis of ethyl acetate, acidic hydrolysis will give you this carboxylic acid. Okay, now let us now discuss the synthesis of dicarboxylic acids. Okay, that is there for a syllabus also. Let us discuss the synthesis of dicarboxylic acids. Okay, let us take an example of succinic acid, preparation of succinic acid. Hope you know what is succinic acid. So sodium salt of ethyl acetates, it is treated with bromoacetone. Okay, and the product upon hydrolysis gives you dicarboxylic acid. Let us discuss the preparation of succinic acid, that is a dicarboxylic acid. So far we have discussed the synthesis of ketones as well as the synthesis of carboxylic acid. So another example we will take of dicarboxylic acid. Compounds containing 2 COH groups are called as dicarboxylic acids. So we will go for the synthesis of dicarboxylic acid. In that, the particular example we will take a synthesis of succinic acid. We will take a synthesis of succinic acid. Hope you know the structures of succinic acid. Okay, so succinic acid is this: CH2, CH2, COOH, COH. This is succinic acid. Okay, let us target the synthesis of succinic acid. Let us target the synthesis of succinic acid. Now, so ethyl acetoacetate is taken. I will just draw the structures of ethyl acetate in the other fashion. That is CH2 will be center. Then we have C double bond O CH3. Hope now you are familiar with the structure of ethyl acetate. C double bond O OC2H5. This is the structure. Hope you know this. CH3 C double bond O CH2 C double bond O C2H5. This is ethyl acetoacetate. Okay. This is treated with sodium ethoxide. You know that sodium ethoxide is a base. What it does, it abstracts a proton. This acidic proton is what it accepts, resulting in the formation of sodium salt of ethyl acetoacetate. So you get CH minus C double bond O CH3 C double bond O C2H5 is what you get. Na plus is what you get. Right now, then this molecule is treated with bromoethyl acetate. It is treated with bromoethyl acetate. Okay, that will give an intermediate that on hydrolysis, acidic hydrolysis, will give succinic acid. Okay, this is treated with bromoethyl acetate. So just this is treated with bromoethyl acetate. Br CH2 C double bond O OC2H5. Okay, CH3 C double bond O OCH2H5 is ethyl acetate. CH3 C double bond O OC2H5, a bromo substitution. So this is bromoethyl acetate. So what happens is this, you know that this will be a slight positively charged because there is an halogen atom. So this negative charge attacks it. Okay, resulting in the formation of a compound. And the compound goes like this. CH3 C double bond O CH. Okay, I'm writing this molecule CH3 C double bond O, this CH, C double bond O OC2H5. CH3 C double bond O CH, C double bond O OC2H5. This will attack it. There will be a bond between this and this. So it will be CH2 C double bond O OC2H5. This is what you get. We're getting this, right? See, this is ethyl acetate. When it is treated with sodium ethoxide, removal of proton takes place, and this. Okay, now, so what has happened here? CH3 C double bond O CH, C double bond O OC2H5. Right? This is the ethyl acetate molecule where the proton is removed. So this anion will attack this carbon and it will form bond with it. So we will get CH2 C double bond O OC2H5 is what you get. Then it is subjected to hydrolysis. Okay, so it is subjected to hydrolysis. Okay, this on hydrolysis. Okay, we can treat it with concentrated NaOH followed by acid hydrolysis. Okay, let us see the products that are generally obtained. Okay, so this bond breaks. Okay, this bond breaks. This bond breaks and this bond breaks. Okay, this forms acetic acid. This will give you succinic acid and this will give you an ethanol molecule. Okay, so what happens is H OH, here H OH, H OH. This is what happens. So this bond breaks, H adds here, what you get? You get C2 H5OH. This bond breaks, H adds here, you get 2 molecules of ethanol. This bond breaks, OH adds here, so you get CH3 C double bond O OH. So the remaining is this part now. This part. Now H adds here, so it will be CH2. We have CH2, then we have C double bond O OH, C double bond O OH. So this is how you end up in getting succinic acid. You get succinic acid. Okay, very simple reaction. First the proton is removed and then it is treated with bromoester. So this bromoester forms bond with this and then a simple hydrolysis will give this molecule. So this carbonyl carbon next bond breaks. All the carbonyl carbon next bond breaks. Carbonyl this bond breaks, this bond breaks and this bond breaks. So here OH gets adds up, here H. So you get acid, hydrogen here, OH, H. So you get dicarboxylic acid. So this is how generally succinic acid is prepared from ethyl acetate. Okay, now next one is the synthesis of heterocycles. The synthesis of heterocycles from ethyl acetate is what we are going to discuss. Okay, synthesis of heterocycles. Now, so ethyl acetate can be used in the synthesis of heterocycles. The first we are going to synthesize uracil compound. it can be used in the synthesis of heterocyclic compounds. First, we are going to synthesize 4-methyl uracil. 4-methyl uracil, what we are going to synthesize. Okay. Ethyl acetoacetate, especially the enol form. I hope you know what is a keto form and a enol form. Enol form of ethyl acetoacetate reacts with urea in presence of POCl3 to give you 4-methyl uracil. I will just draw the structure of that urea. It is C double bond O. It is NH2. I will write it as NHH. NHH. NH2CO, NH2 is urea. NH2CO, NH2 is urea. Whenever it is treated with ethyl acetoacetate, hope you know ethyl acetoacetate. Okay. So I will write the enol form of that ethyl acetoacetate. Okay. CH double bond C, CH3 OH, C double bond O, OC2H5. So you know ethyl acetoacetate, this is ethyl acetate, CH3, C double bond O, CH2, C double bond O, OC2H5 is ethyl acetoacetate. If an hydrogen protonates here, there will be a double bond here. You know this, right? So hydrogen protonates here, so there will be this. So this is an enol form. That's what I have written here. See, CH3, this CH3, OH, C double bond CH, this one, and the remaining part. Whenever it is treated with this, so in presence of POCl3, simply condensation takes place. Okay, with loss of water molecule. Water goes off OHH. From here, ethanol goes off C2H5OH. A simple condensation takes place, resulting in the formation of this compound. C double bond O, as usual. We have NH. We have NH. Then C double bond O, CH3, CH double bond CH. So this is 4-methyl uracil. A simple method of preparation. So simple, when urea is treated with ethyl acetoacetate, the enol form undergoes condensation to give this compound. So this is 4-methyl uracil. Another heterocycle, that is antipyrine, can be prepared. So antipyrine also can be prepared by ethyl acetoacetate. Let us see the preparation of antipyrine. So ethyl acetoacetate, that is CH3, C double bond O, I will write it here, C double bond O, CH2, C double bond O, OC2H5. When it is treated with phenylhydrazine, hope you know what is phenylhydrazine. It is NH2, NH, C6H5, a phenyl group. C6H5, NH, NH2 is phenylhydrazine. When it is treated with phenylhydrazine, it undergoes condensation, combination of with loss of water molecule to give you an intermediate compound. I'll just write the structure of this intermediate compound. CH3, C, there is a bond here, double bond N, the remaining part, NH, C6H5, right? This part, the remaining part, CH2, C double bond O, OC2H5. This is the intermediate form. So this undergoes cyclization. Cyclization with the loss of ethanol. So C2H5OH and H goes off here. Okay, so a bond between nitrogen and carbon is formed. This contains lone pair, hence it attacks this. So loss of this takes place and loss of hydrogen takes place, resulting in the formation of this compound. You have CH3, C, double bond N, C6H5, CH2, C double bond N, and this is antipyrine. Okay, so this is the synthetic application of ethyl esteoacetate in synthesis of antipyrine, in the synthesis of 4-methyl uracil, carboxylic acid, as well as ketones. Thank you.